Greetings. Solving problems of engineering thermodynamics could be a difficult task. The reason is because we are talking in thermodynamics, we are talking about a different language. Of course, many things in the nature are what we experience. Say, if a teacup cools down, then it's a familiar experience. But how do we express it scientifically? Then heat transfer comes in, then temperature comes in, and just relating that problem of cooling a teacup to a thermodynamic language is difficult. It's just like learning a different language. We have different words, you have different grammar, and therefore expressing what is quite usual for someone to do in its own native language would be quite difficult to be expressed in a different language. And that's the same with thermodynamics. We have learned and we have known many things from our experience. But now we want to express them in a thermodynamic language. And that is where the problem comes in. How to translate what we already know in our experience, we can feel it into a thermodynamic language, and how to apply it to different instruments that we perhaps know, or some of them we perhaps don't know. So the problem we want to focus on is how to solve, how to solve problems of engineering thermodynamics. And I suggest 5 steps, which these 5 steps help us do that fairly regularly and straightforward. I wouldn't say that it's simple. Still, it gives us somewhere to start. In fact, it gives us 5.5 places to start our solution and start. It gives us a systematic approach to the thermodynamic problem. And the first step is to find properties. Properties you do not know. You do not know. Every thermodynamic problem starts with some sort of set of properties that you know, and there are a number that you don't know. Find. Usually, 2 properties are given, and but you need the rest of them. Usually, pressure and temperature are given, and you need a specific volume. You need entropy, you need enthalpy, you need a specific energy, and all the rest of them. So see how many properties you can find. Do them. That's a very time consuming job. Actually, many times in the exams, just this step takes half the student time just to fill in the property table. There are there are property tables which you could use, or you could use applications on your cell phone. There are many applications which give properties for different, for especially Steam is very popular, but there are also other applications which give properties of other substances. There are also you could also search in internet for tables of different tables for different substances, or in the books, many thermodynamic books have table of properties at the end of it. But you should fill a table for your own problem, and that is a difficult task. It's a very time-consuming task. 2. Draw a diagram. Draw a diagram. It's a very key point because it would give you a picture of the process. It will not only give you a picture of the processes, but on the diagram, you would say where point one is, where point two is, where point three is, where each process is, and that helps you to remain consistent throughout your solution. So drawing a diagram gives a good picture. You might not be able to complete that diagram to start with, or you might not be able to draw a correct diagram from the beginning. That's no problem. Do it, then return to it and correct it. 3. Decide on the control volume. Decide on the control volume. Decide what do you want to study. Decide on a boundary and see what you have inside the boundary and what goes in and out of that boundary. That's the thermodynamic way. You don't have to stick to it throughout the solution. You might decide on the control volume and then for simplify equations for your problem. You see, you can decide on the control volume and write equations for that control volume and for that process. Then change your control volume and then simplify equations for that new control volume that you have selected. But still, you have to do it. You may you may change your control volume if you found that the previous control volume does not solve your specific problem. That's no problem at all. You could do that. You could simplify your basic equations um, for the new control volume you have selected. That's no problem either. But still, remember, decide on your control volume and then simplify your equation for that process for that control volume. The equations that we mean are the different laws of thermodynamics. Throughout any course that you take anywhere, you will learn these equations. The three equations are the main laws are the mass conservation, which basically is telling us that the change of mass inside the control volume depends on the incoming mass and outgoing mass, and nothing else. The white here has a specific meaning. It means that there is nothing to the right. Nothing else can change mass inside the control volume except the mass going in and the mass going out. Second, the change of energy inside the control volume depends on the energy going in with the mass going in, the energy going out with the mass going out, but more than just the mass going in and out, like the previous equation. Now we have two other terms. Heat and work, heat transfer and work can also change energy. They don't include mass. You don't need to transfer mass to be able to transfer heat, but still, you can transfer heat and you can do work independent from the mass that goes into the control volume or goes out. They are different things. And the third equation, which is the second law of thermodynamics, tells us that the entropy inside the control volume changes with the entropy going in, the entropy going out, heat transfer, and the entropy generated through the process. It's interesting. What we have in these equations, and I'm giving you a total picture, a total summary, which you might have studied it by now or you might not, and you will gradually learn these equations throughout your course, is that doesn't matter. I give you a total picture. This is all thermodynamics is about. If you only need one equation, that's fair enough. Leave the other aside. But you might need two or more, you might need all three of them to solve the problem. And as you progress in learning thermodynamics, then you would also learn how to apply these equations together. But this general structure is the same. There is there are three properties inside the control volume: mass, energy, entropy. How do they change? They change with the mass in and with the mass out. What else can change a property inside a control volume through a process? These are three: heat transfer, work, entropy generation. And that is the general structure that uh, every thermodynamic problem should take, and what is our art, our ability to solve problems is to translate every physical description to these equations and to this language. So the final step would be add all previous steps towards a final solution. And that's all the steps you need to take to solve a problem, except the fifth one, which has to come at the end. But the other four can precede each other, can be incomplete, and then you can return to them to complete them. But a complete problem uh, solves all these steps together and in harmony. It means that they have to resolve similar, they have to produce similar results, they have to match, and your diagram should match your equation, should match your properties, and all of them should come together. You might then do one step wrong. No problem. You have to return to it and do it and correct your step. So, what we shall do from now on is try to apply these five steps to every thermodynamics problem. Before I go to problem solving, I give you one advice. Don't go for solutions manual. You see, the point is this. Think if you watch soccer. Many of us like soccer. And if you watch soccer, you watch one game, two games, three games, four games. That won't make you a soccer player. Will it? It won't. It won't make you a soccer player. You would be a soccer player. You would be a better soccer player if instead of watching all good soccer that is on TV, go to the field and kick the ball. That would be far more better than watching other people playing soccer. Solution manual just give a solution. You could watch all solutions. You could watch all of my videos. I wouldn't give you many videos, but you could watch every video, you could watch every solution, but nothing replaces your own work and your own solution. The question many students ask is, how do we know if we have done it correctly? And the answer is very simple. When you know that you have done it correctly, then you have learned. And that doesn't happen overnight. You might solve your first problem wrong. The second problem might be a bit better. The third problem, when you solve, you would know that you have made some mistakes before, but like anything in life, you would gradually improve and you find the confidence that now you are in a position to solve thermodynamics problems. So do it yourself. This is a new language. You have to practice till you fully learn it. Finally, I want to introduce a few good books which I shall be using for my problems. I shall be using for um, tables and also for lectures if I want to do so. So um, there are different books, and I recommend that if you don't make contact, if you cannot communicate with a book, then try another book and see if you are okay with that one. Usually, the writers are good in some subjects and they are okay with the other. So any writer could write different topics um, better or not better. So see who you can communicate with, who has written a topic better, and then use that book for that topic. Now, the first book I introduce is the one by originally by Van Wylen, now with students and friends, Bergman and Zontag. I've continued the book to its 10th edition. This is a very good book for examples and for problems. The problems are very practical and they introduce very applied cases to for thermodynamic analysis. Solving these problems would be very, very informative and very, you will learn a lot from solving these problems. The second book I introduce is by Moran and Shapiro. I found this book very good with the second law and availability analysis. It also uh, was very good in the type of equations that it used and the way it introduced the equations for mass conservation, first law and second laws of thermodynamics. The other book that I introduced is the one by Yunus Sengel and his friends. This is a very detailed book, many good examples, many good pictures, figures, and also very applied, excellent problems to solve with solutions. And this is a very detailed treatise on thermodynamics. And finally, the very last book that I introduce is by Terence. And the advantage I found in this book was that it gives a special chapter to mass conservation law. And this is what many books don't usually do. They usually treat mass conservation law as part of the first law of thermodynamics or part of a different chapter. And this book gives mass conservation law a special place, and that I found very correct because mass conservation law, although it is very simple, but it has all the necessary elements to introduce different methods for thermodynamic analysis. So if we treat mass conservation law completely well, then it would be okay for you with first law of thermodynamics and also the second law of thermodynamics. So I use these books for figures, sometimes for tables, and often for problems. But I never stick to a problem just to what it has asked. I usually solve problems for different variations, for different possibilities, and see what happens if we change what the problem has given or what the problem has asked, and see how the situation would change. I would suggest that you also when you also solve a problem, don't stick to that problem itself, but try to change different things and be curious on how variations in a problem could help you understand the situations and the methods better, the systems and the methods better. So, this is my introduction. From the next video, I will start to solve problems. Then, see you then.